welcome everybody. Have any of you attended my talk at the Rochester Security Summit? No? Okay, that's good, because I was going to just give you a heads up. This is pretty much a repeat. Alright, so the talk here says common developer crypto mistakes, but I want you to know this is not like some industry consensus of mistakes. These are my own, this is like from my own anecdotal experience of looking at over 7 years, 200 plus projects, about 80 of them design reviews, and about 120 of them code inspections. And it's from like small projects that like say 10,000 lines of code to really large projects like say 8 million lines of code. Obviously the 8 million lines of code have had some kind of assist, you know, SAS tool. All right, so anyways, they say you're supposed to always, you know, start a talk with a joke, right? And so, oops, that's not the joke. I am a joke, but that's not the joke I'm going to tell. So, yeah, the only important thing really about this is you just need to know that I've been around a while, and I'm, you know, really still passionate about development and application security. And I really consider myself more of a developer than an AppSec person, but anyways, the joke. I was going to basically tell you a good crypto joke, but the problem with all good crypto jokes is that they're really indistinguishable from random noise. So, all right. So some of the things that I'm going to cover is, you know, essentially some good news and bad news. There is some good news, thankfully, and then the mistakes in these 4 areas, and then if I have time, which I probably won't, because I ramble on sometimes, but we'll talk about key management, transparent database encryption, and some TLS issues, different than the ones that I just talked about. All right, so the good news and the bad news. Well, the good news is I have not seen developers designing their own crypto for a long, long, long time, so that's great news. And they very rarely implement their own crypto algorithms anymore. In fact, in the past 7 years, I've only seen 2 examples of that, one with Blowfish and one with an algorithm called T, which stands for Tiny Encryption Algorithm. But the bad news is that most of the developer expertise still comes from copy and paste type of things from Stack Overflow. And so they get a lot of things wrong. Particularly, there's a mistake between confidentiality, which basically is what provides the secrecy for encryption, versus authenticity, which is what provides data integrity and can like detect when something has been tampered with. Every algorithm and every cipher mode doesn't provide the same thing. And speaking of cipher modes, most people don't have a clue what those are, and that causes a problem too. So there's basically these extra components called cipher modes, which is how you combine the subsequent blocks of ciphers, and padding schemes, what you do if it doesn't end exactly on a block boundary. And then more bad news is there's a lot of broken crypto still for legacy applications. I mean, you still see, you know, DES and RC4 and stuff and some old things. And even the experts get things wrong still, like OpenSSL and PPG. And I was just recently looking in CVE details, and I counted up in the last 3 years alone, there were 23 CVEs for OpenSSL. And those people have some really sharp crypto guys. I mean, I know some of them. I've worked with some of them, but you know, the code base was kind of ugly, and that's one of the reasons why they're doing the Libre, but SSL on a complete rewrite. All right, so first thing I want to mention, people get random number generator stuff wrong. If you don't have a good source of pseudo-random number generators, of randomness, you're going to have broken crypto. And I don't know how many people were here for the talk, the previous talk, a couple of you. I mean, when Joe talked about the elliptic curve DRGB, that was one of the backdoored algorithms that basically NSA planted in as a random number generator. This shows you basically that, you know, if you have like keys that are based on some random number generator and they can predict the keys, right, it's game over. So cryptographers require random number generators, strong random number generators. So if you're using like java.util.random, that's not as strong, that's not even the CSR random G, it's just a random number generator. Secure random is. The other thing is that when you're using a cryptographically strong secure random number generator, you need to have an unpredictable key, and the entropy, the seed value, has to at least exceed what the internal state of the random number generator is. So if you're going to like do code switches, does anybody in here do code inspections? Good, some of you. How many of you in here are developers? So at least I'm speaking to, you know, either look for these mistakes or don't make these mistakes yourself. Yeah, what you want to look for is like if you're using Java util.random for anything that's related to crypto, like the keys, you know, IVs, nonces, number used once. And by the way, if I don't want anybody to get this deer in the headlights look, so if I'm unclear on a term because I forget to mention what it means or something, please wave your hand or throw something at me, or, you know, long as money. All right, so seeding anything with CSRNG with insufficient entropy. So if you have like an example would be SHA-1 random number generator. That's what you use. That's what the default is in like secure random. It is 160 bits. So you have to give it at least 160 bit seed, right? And that's not generally a problem with the Oracle implementation if you're at least running it on a Linux Unix system that has like dev random and dev urandom, because I think that's what it uses, the seed stuff. So here's an example of how you would do it correctly. I wish I had a laser pointer here, but the important thing with calling the setseed, the secure random setseed, is that you want to do that before calling like next bytes or next long or next int. Now, it turns out, fortunately, that it seeds itself sufficiently well, usually by default. But you might want to, like, you know, if you're going to run it with the same instance of secure random a long time, then you might decide to just reseed it periodically, like every couple billion calls or something. All right, secure hashing weaknesses. What to look for there? Well, there's some completely broken algorithms, and some would say basically, you know, MD2, MD4, MD5. The first two you don't hardly hear anymore. You see people use cyclic redundancy checksums, and then they should really be using a secure hash. That's something else to look for. You should be phasing out SHA-1. I mean, you should have started that a long time ago. Use like SHA-256, SHA-512, or KEK, which is SHA-3. The other thing you want to do is consider what it is your threat model is, right? So when you're like comparing hashes, right, if you're concerned about internal attackers, and this is not a problem with external attackers, just over a WAN or something like that. If that's all your threat model includes, you don't really have to worry about this too much. But it turns out that like a lot of people will base 64 encode the hashes and then use like string equals to compare two hashes, or arrays dot equals to compare two byte arrays. And those are both time dependent. It turns out that before this version of JDK 1.6, the message digest.isEqual was also time dependent, but now it's a time independent algorithm and it's fine to use. The other thing is that you want to make sure, since you're not vulnerable to denial of service attacks, that if you call like message digest.digest or .update, that you make sure that you have bounded the input. If you let somebody call it with unbounded input, right, you're just like, here, this is dev 0, let's suck on this for a while, and, you know, so. The other thing is, a lot of times you see people using hashes as message authentication codes. MAC, a message authentication code, is a keyed hash, where the key is some secret value that's usually shared out of band. And a lot of times some people will put their own, so you you see, like right here, what they'll do is they'll concatenate the message at the end, put a key in. That's bad. That's something that's basically known as a key length extension attack. And so correct use, the proper use is to use HMAC, which is defined in this RFC, and there's a MAC class in Java that basically allows you to do just that. You just init it with a key before you call digest, or update rather. All right. Another thing, if you use basically a secure hash to mask data where it's possible to enumerate everything, right? So an example, sometimes I've seen this in real life where people will go like, oh, I'm not storing in a log file the social security number, I'm storing a hash of the social security number. Well, that's just as bad, because the problem is I can enumerate all the social security numbers, then I can go through your log file and figure out, oh, this social security number is associated with this user, right? So if the adversary can observe the hashes, then they can basically enumerate all the values. So some people a lot of times ask, is using MD5 or SHA-1 ever okay? The best MD5 collision, just to give you an idea, is about 2 to 24 steps, which takes about 5 or 6 seconds on an average modest laptop. Right? You can do this on like 30 seconds probably on your phone. It's okay though to use it in the following cases. If you're just using it as a pseudo-random number generator to generate a random stream, like to generate, say, initialization vectors or something like that. Or if you're using it with an HMAC construct. These three guys, they're cryptographers, proved that basically HMAC security doesn't require an unland hash function to be collision resistant, but only that it has to act as a pseudo-random function, which they do. Any questions so far? Okay. So, symmetric encryption weaknesses. So, you're not using inappropriate algorithms like RC4 or DES. Like DES basically is weak key size, 56 bits. RC4 has got a severe bias in the first 256 bytes of output, which a lot of times allows total breakage. Insufficient key sizes. One of the things that's not immediately obvious is that if you use the triple DES, which is DES EDE, it defaults to 2-key DES, which is 112 bits, unless you have the JCE unlimited strength jurisdiction policy files installed. Now, if you tell it that you want to use a key size with the init, and tell it is tell it to use 164 bits, 168 bits, sorry. Then it would give an error if they weren't installed. The other thing is ASCII generated keys, you see that a lot. And appropriate use of cipher modes, inappropriate use of other cipher modes, which I'll mention a little bit later. And then also, like I touched on earlier, there's confusion about confidentiality implying data integrity. So a lot of times we see examples when we're looking for stuff, people are, instead of generating a secret key the proper way with the key generator, we'll see just a hard-coded key that's either in a properties file or hard-coded in the code. Both of which are bad because, for one thing, you're going to usually put these in your version control and check them in, so a lot of people have access to them. But aside from that, it's just bad because, like, on average, I think it's like the average ASCII password, right, they found is basically only has 3.2 bits of entropy per byte, okay? So instead of the full, you would get, like, so if you had like a 20-some character password, it's like, you know, you're only going to get like 60 bits or something like that. It's not going to be enough. So, you know, generate random keys with the key generator. All right, question for you. Anybody know what the answer to this is? What's the default cipher mode? Okay, answer is ECB, Electronic Code Book. yeah, thanks to Oracle or Sun or whoever you want to blame. There's block modes in symmetric ciphers. They act as block modes or stream modes. The two block modes are ECB and CBC, cipher block chaining. And then pretty much anything else is a stream mode. Any mode, except for ECB, requires an initialization vector, an IV. Stream modes must never, ever reuse the same key pair, key IV pair, okay? Not ever. But one advantage of stream modes is that it did not require padding. So let's talk about a little bit about ECB. Why is it a bad thing? Well, first, it's a raw application of the cipher algorithm, and it's the most commonly misused. First and foremost, because the first thing you do is when you Google for something, right, it shows you an example that's in ECB. It also happens to be the first example you see in most textbooks, and generally people just stop reading as soon as they find the first example. I know I've done that too. I mean, you know, I'm a lazy developer, so why would I do extra work, right? It's the simplest also to implement because you don't have those pesky IVs to bother with. And what do you do with the IV? You know, how do I get the IV around anyways? So, but the weakness is the same plaintext block always encrypts to the same ciphertext block, right? So if you have repeated blocks, you'll see patterns in them. And block replays that are also possible. In other words, basically you can take and rearrange the cipher blocks and replay them back in different orders and stuff. We'll see examples of both of these. So this is a great example from the Wikipedia. But the last image is basically any other cipher mode besides ECB. Looks random. But you can clearly see the pattern in the middle there where they use ECB mode. And you can still see the remnants of the original tux image. Alright, so block replay attacks. An adversary can modify without knowing what the key is or what the encryption algorithm is even. They can mangle messages beyond recognition. They can remove, they can duplicate, they can interchange blocks, right? And sometimes that will allow an attacker to change the meaning of, especially if they know what the message structure looks like. So consider this following example that basically came from Schneider's applied cryptography book, but was actually discussed earlier than that. You have this 8-byte encryption block size. You're going to try to transfer money between two banks. And you're going to, the bank's standard message format is you have a receiving and sending and receiving account number, the depositor's name. The first one is the actual bank identifiers. And then the account name, account number, and amount. Right? So basically this is what ECB looks like. You see that each block is independent of every other block. Right? So that's one of the reasons that's great for doing things in parallel, right? I can do them all 10 blocks at the same time, or 10 blocks at whatever, how many processors I have. But that's also why it allows it to be rearranged. Right? So if you have this attacker malware, he's always the man in the middle agent in the crypto things, and we're talking between the Bank of Alice and the Bank of Bob. Mallory seeds both accounts with some money. And then she transfers some fixed amount of seed money to the Bank of Bob from the Bank of Alice and records the transactions. Right? And we're assuming that they're not using SSL because, hey, we're encrypting everything with triple DES or whatever. Right? Why do I need to use SSL TLS for? Right? So assume that Mallory can actually, get in the middle and act as a active adversary. And so then Mallory repeats it later and looks for identical blocks and eventually sort of figures out what the protocol is and what the block structure is. So now Mallory can go back and insert message blocks into the communication chain, and she basically can take that fixed amount that would be deposited to somebody else's account normally and put in her account number, right? And the two banks, they're going to notice this eventually whenever they reconcile accounts. But at that time, Mallory's already basically skipped town. Right? So this is not something that can be just like defeated by putting in a date and a timestamp or something like that, or a date and a timestamp with a hash. If you just put in a hash, malware can recompute the hash, right? But it could be done with a message authentication code that only the banks know that they share a key for the MAC. So if you're looking for cases of where ECB is used, like in Java, you would look for just cases of where they're just doing get instance, or where they explicitly put in ECB as a cipher mode. And in the case of the get instance call, we call this basically a cipher transformation. So the first part is the cipher algorithm, the second part is the cipher mode, and the last part is the padding scheme. All right. You also want to look for no evidence that an initialization vector is being used, because ECB doesn't require one. So in Java, you're going to look for the absence of something. When it's harder, I understand, to look for the absence of something, but you might want to grep for the code, look for like IV parameter spec, and cipher.getIV. And then you can also check the lengths of the resulting encryption, because generally, when an IV is passed with the ciphertext, what happens usually is the usual case is you prepend it to the ciphertext. So it acts then as the first block, and it's ready to be pulled off and used immediately. So, is using ECB ever okay? Well, yes, but I give that as a qualified yes. All right. This is kind of a complicated situation, so in reality, you're best not to use it at all. But if when you're encrypting less than one cipher block of text, and certain things like block replay attacks and other ciphertext attacks are not feasible, maybe because you have a MAC that you're putting around them, or when you're encrypting random data, for instance, if you're encrypting session IDs, which are UB random, or secret keys, or passwords if they're strong passwords for us to have, yeah, right, because password 0, 1, 2, 3, or whatever, is not ever going to get past somebody as a candidate password, right? And padding is used on an appropriate basis, and as I said, block replays, or in case of asymmetric encryption, say if you're using it like RSA. For asymmetric encryption, ECB is really the only mode that you should ever use. But if you're not sure, look and see if there's a block replay attack, and ask yourself if there are multiple blocks that are exposed to an adversary where the ciphertext can be tampered with. I'm using this word adversary in quotes and italics because it really depends on your threat model, right? If you don't consider an insider a valid threat, and in some companies they don't, then you don't really have to be concerned about that so much. The other question is asked, is block reordering ever going to be failed and detected in some cases, or any cases? If the answer to any of these questions are yes, then block replay is going to be possible and you should avoid it. All right, so I mentioned not reusing rather the same key and IP pair. Stream ciphers and block ciphers operating in streaming modes basically work by creating a cipher bit stream and then XOR it with the plain text. Right? So if we have like the cipher bit stream we call CKIV, and then the message for encrypting would be basically just a message XORed with that cipher bit stream. Right? So let's see what happens when we basically encrypt two different plain text messages, A and B, with the same key and IV. Right? So if you look through and walk through here, it works out to the way that I've suggested. You end up with A XOR B. And the reason for that is because when you XOR something with itself, basically it's all zeros. And when you XOR all zeros with something that's acts like an identity, you get back what you started with. So you basically, the XOR of two plain text messages, A and B, that's like basically the difference of A and B. So what do we do with the XOR of two plain text messages, A and B? Well, if both are written in some kind of normal language, like say they're ASCII character set or something like that, we generally take a guess and use frequency distribution and run what's basically called a crib over top of them to basically be able to guess the likely plain text bits and the frequency increases as we make a correct guess. Modest computers can basically crack this in a matter of a couple of minutes for like modest length messages, let's say, 50 characters or something like that. The more ciphertexts that are created in the same key IV pair and absorbed by an adversary, the better chances they have. The other thing is if you have like fixed messages, like that have a particular structure, or like say they know you're encrypting social security numbers or credit cards this way, it makes it even more trivial, right? Eventually, you're going to get both of the plain text, or at least the shortest plain text. All right, so this is basically what I was just talking about pictorially. I found this example, Dr. Rick Smith, and got permission to use it. So what we have here is basically a plain text image and a random key, and you basically XOR them together, and you get what's over on let's see, which way? On your right. Right, and the close-ups, you can see that basically the send cache encrypted random and the encryption key random are actually two different random bit patterns. Okay, so to recover the original message, we would basically XOR it again with the encryption key, and we get back the original message as anticipated. So now let's do the same thing using the same encryption key with two different messages. So you get what's again on your right in both cases, and you can't really see it from here, but those are actually different random patterns, right? But it's the same encryption key. Now here's what happens when we XOR those two images together. The send cache one and the smiley encrypted. You can see the pattern here, right? So we end up sort of with the diff of the patterns. But it gets worse. If an application is actually doing this and an adversary can decrypt the message on the fly and change it, then they may be able to use a man-in-the-middle attack and actually alter the ciphertext. So like, this is actually called a stream cipher attack, and it's in the Wikipedia example, but basically what they're doing here is they change an amount that was encrypted for $1,000 and they change it with $9,500. Right, so just like increase the amount. So like, you send me a thing that says I agree to pay $1,000 and I change it to $9,500 or something. Not that I would do that. Okay, so this is a detour. There's a thing called authenticated encryption, which does provide both confidentiality and integrity. Integrity is not exactly the same as authenticity, but it's sort of related because the idea is if we know who produced it and we're trusting that recipient, then we basically are also trusting the integrity, and it can detect anything that's been tampered with, though we can't tell exactly what's been changed. But there's three different approaches to trying to do authenticated encryption. There's one encrypt then MAC, encrypt and MAC, and MAC then encrypt. And I'm not going to go into the details, but it turns out that only encrypt then MAC is the only one really that's actually secure. And it's already built into some cipher modes like CCM, GCM, EAX, etc. All right, there's another important thing to remember when you're doing cryptography. Excuse me. Called Horton principle. It's after the Horton heroes of who. It's relevant basically when you're going to say, okay, I'm going to do my own MAC, or I'm going to use authenticated encryption. What data should I authenticate? What data should I include in that integrity check? So what you want is basically, you want to authenticate what you actually mean, not what you actually end up saying. You want to avoid unauthenticated data. Either don't send it across the wire, or include it as part of the authenticated data, but don't send it across the wire unauthenticated if it's anything that needs to be understood. Okay, I made this mistake when I was doing ESAPing in OWASP, where I put the cipher mode in and didn't MAC it, and because of that, somebody could actually change the cipher mode from like CBC to OFB or something like that, and then cause other problems that basically that broke the ciphertext and allowed people to change it. All right, so basically you include the metadata. And there's special ways to do that with like CCM, GCM modes. Okay, so cipher block chaining mode is the most frequently used, and it's one of the things that's good about it is that if you use it incorrectly, unlike streaming modes, it doesn't completely break. It just degrades basically to ECB mode, right? So it has sort of a worst case, but the worst case is not total breakage, right? But used correctly, CBC with a random key and a random IV with padding, and then you HMAC with the encrypted MAC approach. But you see a lot of common mistakes. People will use fixed IVs or predictable IVs like a counter or time or stuff like that, or failure to MAC it correctly, like they don't MAC at all, or they use encrypt and MAC, or MAC then encrypt type of things. So those are things you look for in the code. If you're in doubt, basically you should use authenticated encryption. If you don't, there's a thing called padding Oracle attack with CBC mode that can happen. That was dismissed for a long time, for like 8 years, basically, as only a theory. And then Rizzo and Duong basically came out with the POET software in 2010, and they broke a lot of things like Java server faces and ASPS.NET and a bunch of other stuff that was using this, that had a pattern Oracle in it. All right, so symmetric encryption weaknesses. Assuming that confidentiality applies to data integrity, that's only true if you're using an AE mode. If confidentiality is not required, it's better and faster to just use an HMAC. Turns out CCM and GCM are actually fairly complicated to use, and if you look for examples of how to do it correctly, you won't find any. At least I couldn't find any. So it's kind of all rocket science. I suppose maybe if you look at the Bouncy Castle JUnit test, you might find some, but that's probably about the only place. Okay. Okay, so asymmetric cipher is when you have two different keys, one to encrypt and one to decrypt, like RSA is an example, right? You always have what's called a chosen plain text attack possible. It is not always fatal, but it's always possible with any kind of asymmetric cipher. And the reason for that is it's always assumed that someone else has access to the public key. I mean, there's a reason they call it public, right? So given the fact that basically they can have access to the public key, they can basically they can choose any plain text that they want, encrypt it with that public key, observe the output, observe the ciphertext, right? So that's why we have basically a chosen plain text attack. Right. So, I mean, if I know that there's just a small number of possibilities that you're encrypting, let's say social security numbers and stuff like that, it could be problematic, right? Because I can enumerate all over them, right? So, and I just mentioned that. So basically, if you have a small space to enumerate over, it's going to be a problem. And in fact, this is a real life example. Now, it turns out that this is not a problem. There's two different kinds. I mentioned padding, right? The default padding for like RSA, for example, is PKCS1 in Java. That was turns out it's a very bad padding choice. It's insecure. But if you use optimal OAEP, optimal asymmetric encryption padding, OAEP, that will actually defeat this problem. But I saw a code review in some vendor code where they basically thought they were doing a great job. They were encrypting credit card numbers and storing them in a database. And they were using the default pattern, right? So they just had, cipher.get instance RSA. And I pointed out to them that basically all the credit card numbers now basically could be enumerated. And, so if they had like an insider rogue DBA or something like that, they could grab the ciphertext from the databases. That person could enumerate all of them and figure out what they all were. Right, so, oops, we better fix this. How are we doing on time here? So rekeying. Key management is probably the hardest problem in cryptography. Okay. One of the things is that if you ever look at the PCI DSS standard in 2.0 and later, it says that you must change symmetric crypto keys at least yearly. If you want to blame somebody for that requirement, you can probably point to me, because 1.0 didn't ever, it just said you had to regularly change them. So I challenged them, how often is regularly? Well, I don't know. You know, I said, so, okay, we're going to change ours every 10,000 years. No, you have to do more than that. So, like, they put it yearly. But it turns out that it's a lot more, maybe often than that, right? Because aside from the fact that somebody, that you might have leaked it somewhere, you know, the encryption key might have gotten stolen or whatever. Also, it turns out that there are attacks in general, attack is that if you have a cipher block text of cipher block size bits, that every 2 to the nth over 2, where n is the key size in bits, that you should change the key, right? So in DES and triple DES, which only has a 64-bit block, you should change that. Basically, when I think that if I did my math right, I think that works out to like 257 or something like that gigabits, right? Now, most of the time, if you're just like doing a couple of social security numbers in a database or something, that's not going to be a problem. But if you got like a VPN or you're doing bulk file encryption or something like that, it may be a problem. It turns out, though, that there was actually a real life attack last summer, known as the Sweet 32. Anybody heard of that? It was attack. Matthew Green's blog post has got a really good write-up on the explanation of how all that works. But basically, this was based on not rekeying and reusing the same key stream, but yeah, using the same keys over and over again. All right, so where do you store your keys? Right? Well, ideally, you put them in an HSM or a TPM. But the one thing where we see the most, where I've seen in code reviews, the most failed cases, people put them in a file, you know, in hard-coded, a source code, or a properties file, both of which are under version control again. So, you know, that's going to be a problem. It's better maybe if you let your dev staff, your ops staff rather, choose them, put them in a configuration file, lock it down with the OS, and it's not available to like developers, and only certain very small group of people can get it. But you know, that's a problem because the developers don't want to do that. Well, hey, it's not rocket science. Write a script, let them run it to generate a key. You know. And even they might not, you can just generate it and put it in your properties file automatically. You don't even have to have them edit the file. Better is like on .NET to use the DP API, Data Protection API, and for Java, if you're using Oracle, Oracle's got a WebLogic encryption services, and if you don't have that and you're on Java, I would recommend Java Key Store. That has problems too. I don't have time to go into them. But if you're interested, I can talk about it. Someone can ask me later. Right? Never put the one thing you should not do is don't put the encryption key in the same file as the data that is being encrypted with. So, like for instance, if I have a database password in a properties file, right? Don't put the database key in the same file. That's not good. I mean, it's like making them work a little harder than that. All right. Encrypting data in a database. There are 3 different ways, 3 different approaches to do this. One is to have the database engine itself do it, mostly transparently, right? Another way is to do it via a proxy, using something like MIT's CryptDB, which is sort of considered still experimental, but it's probably much easier than writing your own application code. And then doing it via application code, having an application encrypt and decrypt stuff. From the application perspective, the TDE is very, very simple. It's transparent almost to the application. It's available for Oracle and Microsoft SQL Server, and it probably satisfies, I never checked this, but it probably satisfies the letter of the law for PCI DSS. And it offers TDE both for Oracle and Microsoft offers like encryption at the column and table space layers, but I don't think they call it table space in the SQL server, but at the physical layer, you know. And then you have usually limited cipher suites available, like I think typically it'll be AES or triple DES only. And usually there's like 2 keys, like in Oracle TDE, you have the Oracle wallet, which is like the database master key that gets constructed and passed around. And then that's used basically to decrypt and encrypt the other keys for the individual tables and columns and table spaces. And usually they use CBC mode, but they have to use, almost of the time, they have to use the same initialization vector all the time. Now, the good thing, like I said, about CBC mode is that it breaks sort of gracefully, you know, worst cases like ECB mode. But the reason you have to use the same IVs, if you, like say, encrypt 2 different credit card numbers with 2 different IVs, you end up with different ciphertext. All of a sudden, that breaks indexing, right? Because now you don't have a unique entry. And so there's a couple cases where you can't use the TDE. One is basically where you want to use the result as of an encrypted column as a foreign key into another table. There are some restrictions. You can't use like, what do they call it, the searches with the percent, the wildcard searches, right? So you can't use wildcard searches. So if I wanted to say, search for all the, you know, credit card numbers that start with 1, 2, 3, 4 or something like that, I can't do that, right? You have to enumerate over all of them. So if you need to do searches like that, you need to take that stuff into account when you're designing your database. Assault basically can be used with these things. It acts as a unique IV. It basically says use a unique IV for this column or whatever that you're applying to. But again, that means then you cannot index it. So it would be okay to have a small number of records, or it's something that you're just always going to do a search based on something else and then retrieve it, then that's fine. So what's your threat model here? Why does TDE fail? Well, it fails because, first of all, unless you basically set up appropriate database views, if any application has access to that database table or column or whatever, and that happens to be open, or they can access it and open that database, right, then they have access to the encrypted data, right? So that's one of the reasons why we say, hey, you know, restrict that column. This other application over here doesn't need to see this encrypted data, because it's not really encrypted if they can access that column, right? So, and then backups is the other issue. Depending on how it's done, you may end up with dumping the database out actually as plain text. So you need to be concerned about that. Generally, the data that we're encrypting in the database is small, you know, like credit card or social security numbers or some kind of health information or something like that. It has a particular format, and so we have limited possible values. And that also is a problem for the same reason, basically, I mentioned enumerating things. And like I said, in normal cases, we don't use assault because we want it to be able to be indexed. So the same enumeration concerns basically are possible there. So what exactly is TDE good for? Well, like I said, it probably covers the literal law of PCI DSS, but really what it's protecting is basically an attack which you would call, it would be similar to like using full disk encryption on a laptop, right? So somebody basically has a laptop that's in hibernate mode or turned off or something like that, and then somebody steals it out of the back of your car and you get the data. So if we're talking about like somebody basically, you have like an offline backup copy of a disk, right? And somebody does a smash and grab of that disk drive and runs out the door with it, you're safe. But that's pretty much the only case, the only scenario really that TDE covers. All right, SSL socket and subclasses or subclasses of it that get created by SSL socket factory don't have hostname verification or certificate pinning. So what that means is that they don't verify, like you say, I'm going to go to foobar.example.com, it doesn't actually verify that it's connecting Like, so it gets basically, it gets a TLS server-side certificate back from it. And it should say on the CN, right, it should say foobar.example.com. It doesn't do this. Because it doesn't do this, man-in-the-middle attacks are possible. We, 15 minutes. All right, I'm going to do this slide, and then basically I'm going to take questions. All right, so there's two possibilities here. One is that you can implement, you have to implement either your own subclass of SSL socket, or the other one is you can create an SSL socket context. If you're doing this over HTTPS, however, there's a better solution. Use HTTPS URL connection. The reason why I see this is because, you know, I was talking about legacy code and problems in legacy code. This is, when they did HTTP URL connection, they did not do a corresponding HTTPS URL connection. It didn't come out until like a couple years later. And so people started wrapping their own. And so you see this a lot in old systems, and you also see it in cases where I want to use SSL, but I don't need to use HTTP, right? So I'm just talking a raw socket or its own protocol or something like that. So I'm going to end here so we have some time for questions. Does anybody have any questions they want to ask? Yeah.
Do you have any non-Java hints, like for? I know a lot of the information you just covered was pretty general, but do you have recommendations for libraries and stuff in like C or C++?
There is, and let me jump to the, here. Okay, so if you look in here, there's some examples like that. This is the OWASP dev guide. It's still a work in progress, and if anybody's interested in giving feedback, we'd certainly be interested in receiving it. But this is, like I said, a work in progress. This basically covers .NET and Java both. Any other questions? Yeah.
So you mentioned earlier code inspection, and we do a lot of that in the form of like code review as code is being developed. But one of the more daunting tasks that I face is when I move on to a new project and you have to evaluate the whole project. There's potentially hundreds of thousands of lines of code. What's the lowest hanging fruit that you've seen most often that people can look out for when reviewing?
Oh, just the use of ECB mode, because they don't realize that that's the default, number one. And number two is people don't realize the dangers of it. And number three is this, like the first example that you encounter when you Google for it. Okay. You had a question over here?
Yeah, I was going to ask about like the implications on Android and like the mobile threat model of like a lot of the things that you're talking about, like the SSL sockets that you need manually without the name verification. It's always a problem with Android.
In general, with SSL, because you don't know who's controlling your DNS, right? There's a technique called farming. It's spelled PH, like phishing is, which basically is like a DNS hijacking attack if you're like on an open Wi-Fi or something like that. And so somebody will return their own foobar.example.com IP, right, that gets you to their thing where basically host name verification will work because they've just signed it with a different, you know, CA is not aware that somebody else signed the original foobar.example.com. So in that particular case, what we recommend for like mobile applications is to do what's called certificate pinning, where you're actually pinning the certificate based on, depends on how you want to do it, there's two different ways. You can either pin it based on the public key, which works good if you want to reuse the key when it expires every year, right? And just get a new certificate issued. Or you can basically pin it based on like the fingerprint, the SHA-256 fingerprint, or SHA-1 fingerprint or whatever. Yeah, you had a question back there?
Yeah, so early on you mentioned something called something about time-based functions and not time-based functions.
Yeah.
And how the time-based functions are vulnerable. Could you go into
All right, so what happens is when you're doing, this is only, like I said, it's not something which is susceptible over a WAN or a LAN generally because of network lag and jitter. Basically, you know, it's in that uncertainty that you can't basically rule it out. But what happens is, if you basically compare two hashes and a time-based thing. The way that, like say you have 160 bits, right? That's 20 bytes of code. The way that it'll compare the things is like 1 byte at a time, right? You can actually, if you have like local timing hooks, you can like say, oh, this one only went through 18 bytes, this one went through 12 bytes, this one went through 11 bytes. And so you basically can use that kind of as an oracle to detect information about whether the paths or whether the hashes are the same, and then work to like keep on guessing and say if it's a password hash if you're trying to attack, right? To guess the password at a different time, observe it again, and basically see how far it goes through. And there's actually been cases where local system password authentication systems have been compromised in this way. Yeah.
So that's sort of a nice segue into my question then. Certainly there's a number of low-hanging fruit in crypto programming for attackers to get. What actually gets exploited in the wild the most?
Non-crypto.
Okay, fair enough. But
I mean,
of crypto, what do we see?
The only case that I've ever seen in the real world, now I'm not saying, you know, we're not talking about the clandestine world here, but where I've seen reported in the wild of attacks on crypto has been with the old Wi-Fi web standard, because that was so bad that, I mean, a child with a Timex Sinclair could break it in 10 minutes. I mean, you know, it's one of those types of things. It was just...
Two guys with a laptop in the parking lot.
Yeah, exactly. So that's the only case that I can really recall in real life where it's been done. Now, certainly people have done and wrote exploits, like I mentioned, Wong and Rizzo, and they have a nice, if you like Google for, and I would encourage everybody to do this, to Google for padding Oracle attack, and watch, there's a couple of demos on YouTube that DeWong and Rizzo did, and like against the ASP.NET view state as an example, and they like break it in, I don't know, it was like maybe 10, 15 minutes, and then that allowed them actually to not only decrypt stuff, but also re-encrypt stuff, because they were able to sort of figure out a clever way to reverse it, and actually figure out what the encryption key was. So it was a quite ingenious exploit, but in reality, it got fixed fast enough that it really never made it to the wild. So I thought I saw a question somewhere over here. Anybody else have a question? Going once? Going twice? You? No? Anybody? All right, well, thank you.